All right, welcome back. So this is another titration problem explanation video, basically. And this is a slightly different than the other video that I made. So this is from the point of view of a weak acid being titrated with a strong base. So this is just sort of the opposite situation. And I've got 4 different situations or 4 different times throughout this titration curve that I want to be able to calculate the pH. So I'm just going to sort of go through and try to go slowly through my thought process for each step. And then if it becomes too long after part B, then I'll make 2 videos, but all of these will be covered either in this video or in part 2. So let's go ahead and get started for part A. The thing that we need to keep in mind is sort of what type of reactions or equilibrium setups are we going to need to solve for whatever's being asked. And before the titration has begun, we just have a weak acid. So like at this point right here, right, that's point A. And at point A, you haven't added any sodium hydroxide yet. So really, we don't need to worry, this first part, it's not even a titration problem, it's just a weak acid problem. What's the pH if I just have a weak acid? So CH3COOH, that's my weak acid. CH3COO minus plus H plus. We know that this is a Ka, this follows the general form of a Ka, and we have an initial concentration of 1.05 molar for our acetic acid. So initially, this is all we're gonna need, 1.74 times 10 to the minus 5th, minus X plus X plus X. So we're just doing a simple weak acid problem at this point in time. Then we could go over here, 1.74 times 10 to the minus 5th is going to equal X times X, that's our products, over our reactant 1.05 minus X. This minus X term is negligible, so when we actually calculate what the value of X is, we should find that it's negligible. There's lots of different ways you can solve for that. You could also just solve this exactly if you've got a fancy calculator. And if you do that, you should get an X value equal to 4.27 times 10 to the minus 3rd. And that equals the concentration of H+, which we can then take the negative log of to get the pH. So pH equals, for this part, 2.37. So again, this is just a simple weak acid type problem. Nothing really funny going on here. We haven't started doing the sort of reaction first part yet. So hopefully that's clear. Obviously, if there's any questions, definitely let me know. So B is the first time we really need to sort of consider a separate reaction first before we deal with an equilibrium. So the reaction that's going to be occurring is going to be this neutralization reaction. This is going to be a reaction that goes to completion. Notice I've got a reaction arrow here instead of these equilibrium arrows. And this is going to neutralize to form water, and then CH3COO minus, which is the conjugate base of this weak acid. And there's no Ka or Kb or anything associated with this reaction because it's a reaction that goes to completion. So we need to know the number of moles, right? So when you see this, what you should be thinking is, okay, well, I know that this is a reaction that goes to completion. So I need to figure out what my initial moles of each of these is and do basically a limiting reactant problem. So we start with 0.0105 moles of this acetic acid, and I'm just getting that from my molarity and my volume, so 10 milliliters of 1.05 molar acetic acid, that's this number of moles, and then 1.8 molar sodium hydroxide. So I'm just writing OH minus, but that sodium hydroxide, that's really the source of OH minus. So if you think about NaOH, that's sodium hydroxide, that's going to completely dissociate into Na plus, which will be a spectator ion, and then OH minus. So really, I'm just really concerned about this OH minus. That's why I'm sort of leaving it out down here. And I think that's a good exercise. The sodium ions, they're always going to be spectator ions, so we just can ignore those. We can just leave them out. Anyhow, 2.45 milliliters of this 1.8 molar, that should give us 0.00441 moles of OH minus, also moles of sodium hydroxide, but again, just leaving that off. And now we're doing a limiting reactant problem. So this is limiting. And I like to sort of just show my stoichiometry sort of work like this, where if this is limiting, it's going to go to 0 moles, and then our 0.0150 moles, I'm going to subtract, we need to know how much of this is going to be left over. We need to know the excess of our acetic acid, so we need to figure that out. So if you take 0.0105 minus this number here, you should end up with 0.00609 moles. And this is the excess, let's make sure that's visible, excess weak acid. And we need to pay attention to that, right? We have to pay attention to that. How much weak acid do we have? Now, we are also going to be forming 0.00441 moles of our weak base. So this is weak base formed. So at this point in this titration, we're going to have a buffer, right? We're going to have considerable amounts of our conjugate weak base and our conjugate weak acid. So that's sort of the classic definition of a buffer. And so for this, we can actually use the Henderson-Hasselbalch equation. You don't have to. You could, plug these, convert these to molarities, plug these into a Ka type reaction as your initial concentrations of acetic acid and weak base. These converted to molarities would just go up here as your initial concentrations. You solve for X, you'll get the same exact answer. And I would recommend practicing that to make sure you're seeing, how that works. But you can also use the Henderson-Hasselbalch equation, which is what I'm going to show here. So we're looking for the pH. The pKa is just going to be the minus log of the Ka that we have here, minus log 1.74 times 10 to the minus fifth, plus the log. And now I'm just going to use these number of moles. And that's probably not the best practice to do that, but it works, so I'm going to do it. I know that this is probably really hard to see. Sorry. 0.00441, that's this number of moles of base. 0.00609, that's this number of moles of my weak acid. And then when I calculate that, that should end up being 4.62. So that's my pH for part B after I've started to add some of the sodium hydroxide to my solution. So I think I'm just going to continue on and do this whole thing in one video. Hopefully you can read this. This is the base, this is the acid. And again, I used moles. Let me put a little note here. Okay to use moles when we are talking about our Henderson-Hasselbalch equation, and that's just because it's a ratio. It's a ratio of base to acid. So as long as you're consistent, it's totally fine. So C at the equivalence point. So for C, first things first, we need to consider, again, this reaction. We're going to be adding in sodium hydroxide to get to that equivalence point, plus CH3COO minus 0.0105 moles, 0.0105 moles. So this is going to be my starting point. I know that I'm starting with this number of moles of weak acid because that's our 10 milliliters of this 1.05 molar. So we know that that's our starting point. And then at the equivalence point, the definition of equivalence point is that this number of moles of OH minus will equal this number of moles of acetic acid. So we know that we have to be adding 0.0105 moles of that sodium hydroxide. And then from that, we can actually figure out what the total volume is. So if we know that we have 1.8 molar NaOH, we can use that information to figure out, okay, well, to get to that equivalence point, we need to add 5.83 milliliters of sodium hydroxide. So, take this number of moles, divide by this molarity, you're basically using it as a conversion factor to get to what volume of sodium hydroxide you need to add in order to get to that equivalence point. Therefore, we can say that the total volume will be that 10 milliliters plus the 5.83 milliliters equals 15.83 milliliters for this solution in part C. And that's going to be important because that's going to give us the molarity of our weak base that's formed. So this weak base, 0.0105 moles, will be formed. So as this gets consumed, we're forming a weak base. And then that weak base will then continue on to react in a KB type reaction, so CH3COO minus. That's going to be what's present at equilibrium, and that's a weak base. So that since it's a weak base, it will participate in this KB type reaction and dissociate a little bit to form OH minus, or I guess react with water to form some OH minus. But we need to know what our initial concentration is here. So the way that we're going to get this initial concentration is from the number of moles divided by the total volume. So that's why it's important to be able to figure out what that total volume is, because we need to know what the concentration is. 0.663 molar is our initial concentration that we'll then plug in here for our initial concentration, 663 molar, minus X. Then we're just running this ice table as a normal KB type problem. So we've sort of converted this problem. Initially we were starting with a weak acid. I guess here we're starting with a weak acid. But at the equivalence point, if you're starting with a weak acid, at the equivalence point, you've sort of converted it all into a weak base. And then we need to consider this KB type reaction. So now just finishing this off, and we can solve for the KB using the Ka. So keep in mind that Ka times Kb equals Kw, so we can convert. So then in any case, what you should end up with for this problem would be 5.75 times 10 to the minus 10th, that's the Kb, equals X times X over 0.663 minus X. That's going to be negligible. We can solve for X, and we should get a value, let's see if I wrote it down over here, 1.95 times 10 to the minus 5th, and that equals our OH minus concentration. So be really careful, right? Whenever we're doing a KB type problem, that X value is the concentration of OH minus. So then that, when we go from here, we'll go POH first, and then pH 14 minus the POH is the pH. Keep it all straight, 4.71. So if you just take the negative log of this number, that should be the POH, and then 14 minus this number, 9.29. That should be the pH that we're trying to report for part C. Now for part D, I think I'm going to try to fit in part D right in this little space. It's not going to take very much space. So for part D, we need to know what the concentration of excess OH minus is. So that's sort of the key. How much extra OH minus am I putting into my solution, to solve for what's going to happen? So after the addition of 10 milliliters of sodium hydroxide, that's extra OH minus. So if you add extra strong acid or extra strong base, the resulting pH of the solution is only going to be dependent on the amount of excess OH minus. So there's a number of ways to do this. Basically what I did is I figured out how many moles do I put in initially. So 10.00 milliliters of 1.8 molar. If you convert that, you should find that you were adding, I guess I didn't write that number down, but let's just do it real quick. So 0.01 times 1.8 is 0.018 moles of OH minus. That's the total number of moles. And then what I'm going to do is I'm going to subtract 0.018 moles OH minus the number of moles of acetic acid that you start with, 0.0105 moles. Because some of that OH minus is going to be consumed, right, as it does this reaction to get to the equivalent point. And then whatever's left over, that's going to be our excess OH minus. So that equals, that number I did write down, 0.0075 moles of OH minus, which is in excess. I'm going to divide that by the total volume, 0.020 liters, total volume. And that will give me the concentration of OH minus equals concentration of OH minus, which equals 0.375 molar. That's present, and that's going to determine what our pH is for our solution. We don't actually need to do any sort of reaction. I guess you could sort of imagine doing this type of reaction where this acetic acid is the limiting reactant. But what's important is the amount of excess OH minus. And there are other ways to figure out, what the excess number of moles of OH minus will be, but I think this makes sense. So now POH to pH, right? So negative log of this, and then 14 minus, just like we did over here. So your final answer for your pH should be 13.57 for part D. All right, hopefully that all makes sense. If it doesn't, let me know. But this is, it's a lot, right? It's a lot for one problem, but we should definitely be able to do this. All right.